Have you ever wondered if this life, this world, this version of reality is but one page in an infinite cosmic manuscript? Today, I will tell you the story of the multiverse, a tale of boundless dimensions, of mirrored destinies, of realities, stacked like invisible books in the library of everything that ever was or could be. If this awakens a spark in you, if your curiosity stirs like stars whispering across space, then like, share, and let the exploration begin. Imagine the universe not as the entirety of existence, but as a single bubble floating in a vast foaming sea. This bubble, our cosmos, glows with stars and galaxies and the physics we know. Yet beyond its shimmering skin, there may lie others, countless, varied, alien in form or familiar in pattern, birthed from the same primordial breath or spun from different rules altogether. This is the multiverse, a vision where infinity becomes not a number, but a landscape. The seeds of this idea were planted not by poets, but by physicists. At first, the universe was thought to be all-encompassing, an endless stretch of space and time expanding from a singular, explosive origin. The Big Bang was the cradle of everything, but as our tools grew sharper, our theories more ambitious, strange questions began to arise. Why do the laws of physics appear so finely tuned for life? Why does the universe look so uniform in all directions, as though some grand symmetry governs its breadth? Inflation theory came forth. The idea that the early universe expanded exponentially in a fraction of a second, stretching space itself faster than light. This rapid inflation could have smoothed out irregularities, giving rise to the uniform cosmos we see. But it also hinted at something far more radical. If inflation occurred once, could it happen again and again, in regions of space disconnected from each other? Could pockets of space inflate independently, each birthing a universe of its own, each with its own constants, particles, and physics? This is eternal inflation, the first rigorous proposal of a multiverse. In this vision, our universe is but one island in an archipelago without end. While we bask in our sun's warmth and gaze at familiar constellations, other universes may swirl with stars of different hues, or none at all. Time may tick differently there. Gravity may be weaker. Light may bend in unexpected ways. The multiverse becomes not just possible, it becomes, in some interpretations, inevitable. But inflation is only one path to the multiverse. Quantum mechanics, the strange and unpredictable theory that governs the microscopic world, offers another. In the quantum realm, particles do not settle into fixed states until they are observed. A particle may spin both left and right, exist, in multiple places, or pass through two slits at once, until a measurement is made. This mystery gave rise to one of the boldest hypotheses in modern physics, the many worlds interpretation. According to this view, every quantum event spawns multiple outcomes, each realized in a different branch of reality. When a photon chooses one path, the universe splits. When you flip a coin and it lands heads, there is a you in another universe watching it land tails. This is not metaphor. It is a literal reading of quantum math. The cosmos becomes an ever-branching tree, with trillions of leaves unfurling every instant, each representing a different version of events. What does this mean for identity, for fate, for the choices we make? Are we mere echoes in a chorus of selves? Or does this infinite replication diminish the meaning of our singular lives? These are not questions that equations answer, but they pulse beneath the theories like heartbeats under skin. Beyond inflation and quantum mechanics lies the strange architecture of string theory, a framework that suggests all matter and forces arise from vibrating strings in a higher dimensional space. In string theory's equations, extra dimensions fold upon themselves, hidden from our senses. The energy of these curled-up realms shapes the behavior of particles, giving rise to different possible universes, each defined by how those extra dimensions are compactified. There are more possible configurations than atoms in the observable cosmos. This landscape of string theory is a multiverse in itself, a mathematical terrain where universes emerge not from chance, but from the vastness of possibility. And perhaps through cosmological inflation, these possibilities become real, instantiated as separate worlds, unreachable but real. Still, critics of the multiverse point to a haunting flaw: testability. If these other universes lie forever, beyond our horizon, how can we prove or disprove their existence? Science, they argue, must be falsifiable. The multiverse risks slipping into metaphysics, beautiful and bold, but ungrounded in observation. Yet others counter that the multiverse may leave subtle fingerprints. If a neighboring universe collided with ours in the early stages of inflation, the cosmic microwave background, the afterglow of the Big Bang, might bear the scars. Patterns in temperature, unexpected anomalies, could hint at other realities, brushing against our own. Even without direct contact, the multiverse helps explain the fine-tuning of our universe. Why is gravity just strong enough to form stars, but weak enough to allow life? Why do particles have the masses they do? In a multiverse, these values are not fixed by necessity, but by selection. We live in a universe that allows observers, because only in such a universe can the question even be asked. This is the anthropic principle, controversial yet powerful. In a cosmos with countless permutations, most will be sterile. Some will explode too fast. Some will collapse too soon. But a few will be just right. And in those, life emerges, stares skyward, and begins to wonder. The multiverse reframes our understanding of reality. No longer is the universe a singular cathedral, with one path, one history, one truth. Instead, it is a cathedral with infinite corridors, each echoing with different hymns. Some corridors may resemble our own, with familiar stars and planets. Others may shimmer with unknown physics or exist in dimensions beyond our grasp. What becomes of purpose in such a reality? Does the vastness diminish us or elevate us? Perhaps both. Perhaps in the face of infinite worlds, our actions carry both less weight and more wonder. For in this vision, each choice is not erased by alternatives, it is joined by them. Each moment becomes a thread in a tapestry too grand to see, too intricate to chart, yet no less real. And so, the story of the multiverse begins, not as a conclusion, but as an opening. The questions multiply, the implications ripple, and somewhere, in the silence between stars, other universes wait. Strange, silent, vast. To grasp the multiverse is to stretch the imagination beyond ordinary bounds, to embrace a cosmos where the familiar laws of nature become but one thread in a tapestry woven from countless possibilities. It is to envision not a solitary universe, but a plenitude of realms, each a universe unto itself, each governed by its own set of physical laws, constants, and histories. Such an idea challenges the very notion of reality as absolute and singular, inviting us to consider a boundless ensemble where everything that can happen does happen. One compelling framework arises from the landscape of cosmology, the study of the universe's origin, structure, and fate. Modern cosmology reveals a universe expanding at an accelerating pace, permeated by mysterious dark energy, and shaped by the quantum fluctuations that seeded the galaxies. Yet the precision of its measurements also highlights profound puzzles. Why does the cosmological constant have the small positive value that allows galaxies to form? Why is the universe so uniform on large scales, yet rich with complexity in smaller ones? Enter the concept of the multiverse through inflationary cosmology. The theory of cosmic inflation suggests that in the earliest fractions of a second after the Big Bang, space itself expanded exponentially. This rapid expansion smoothed out irregularities and set the initial conditions for our universe. But inflation once started need not end everywhere at once. Some regions may continue inflating eternally, spawning bubble universes in a cosmic froth. Each bubble represents a separate universe, possibly with different physical constants and laws. This eternal inflation scenario leads to a fractal multiverse, an endless cosmic quilt stitched from innumerable universes, some like ours, others dramatically different. Our observable universe is but a bubble in this grand cosmic foam, isolated from others by vast stretches of inflating space. The richness of this picture extends beyond space and time. Each bubble universe could be governed by variations in the parameters that shape particles, forces, and interactions. The fine structure constant, the mass of the electron, or the strength of gravity itself might differ. These variations would render some universes hostile to complexity and life, while others could harbor unimaginable forms of existence. The multiverse thus provides a context for the puzzling fine-tuning of our universe. The physical constants seem exquisitely set to permit stars, chemistry, and life to emerge. Without this delicate balance, complexity would be impossible. Instead of invoking design or coincidence, the multiverse suggests a vast ensemble where all possibilities unfold, and we find ourselves in one of the hospitable pockets simply because only here could observers arise. But what of the very nature of these universes? Are they simply spatially separated domains within a grander space, or do they exist as wholly disconnected realities? Some theories suggest a vast meta-universe, or bulk, in which universes float as bubbles. Others, particularly from quantum mechanics, imply that universes are branching pathways, parallel realities born of every quantum choice. The many worlds interpretation of quantum mechanics casts reality as a continually splitting wave function. Every measurement or quantum event causes a bifurcation, a universe in which outcome A occurs, and another where outcome B happens. This implies a staggering multiplicity of worlds, unimaginably numerous branches of reality, coexisting in superposition but effectively isolated from each other. If true, the many worlds view radically reshapes our understanding of causality and identity. Every decision, every quantum event births alternate selves, each experiencing a different course of events. Our subjective experience traces a single thread through this vast branching tree, unaware of the countless other lives unfolding in parallel. This picture connects profoundly with philosophical questions about free will, fate, and meaning. Does the existence of multiple selves dilute the significance of any individual life, or does it enrich existence, revealing a cosmos far grander and more intricate than we had imagined? Beyond quantum mechanics and inflation lies the theoretical edifice of string theory, an attempt to unify all forces and particles into a single framework. String theory posits that fundamental particles arise as vibrations of tiny, one-dimensional strings embedded in a higher dimensional space. These extra dimensions, compactified in complex shapes, determine the properties of particles and forces. The string theory landscape is vast, with potentially 10,500 or more different ways to curl up extra dimensions. Each configuration corresponds to a different vacuum state, essentially, a different universe with its own physical laws. If realized cosmologically, this landscape becomes a multiverse, a vast array of universes representing all possible low-energy physics. In this framework, the multiverse is not an optional speculation but a natural consequence of the fundamental theory. Our universe's parameters emerge as a random choice from this cosmic lottery, explained not by necessity but by selection among an immense ensemble. Yet the multiverse idea confronts the challenge of empirical testability. By definition, other universes are beyond our observable horizon, inaccessible to direct observation. Does this render the multiverse a metaphysical hypothesis rather than a scientific theory? The debate is ongoing and fierce. Nevertheless, some researchers seek subtle signatures, traces left by collisions with other bubble universes in the cosmic microwave background radiation, or statistical patterns in fundamental constants that suggest an ensemble. Advances in observational cosmology, particle physics, and theoretical modeling may one day bring these clues into focus. Ultimately, the multiverse challenges our place in the cosmos. It invites humility and wonder, framing our existence as one note in a symphony of worlds. Whether these parallel universes are infinite or finite, close or unreachable, real or mathematical, they beckon us to expand the horizon of imagination and embrace the mystery of existence. To venture deeper into the multiverse is to encounter ideas that stretch the fabric of what we consider possible, traversing realms where space and time take on unfamiliar shapes and dimensions. The journey begins with the recognition that our universe is not necessarily unique, but one among myriad others, each manifesting different versions of reality, shaped by the fundamental laws of physics, or by laws altogether unlike ours. One of the most profound contributions to this vision arises from the union of quantum theory and cosmology. Quantum mechanics reveals a world that defies classical intuition, where uncertainty and probability replace determinism. Here, particles exist in superpositions, multiple states simultaneously, until measured or observed, when a single outcome crystallizes. This quantum uncertainty becomes pivotal when paired with the inflationary model of the early universe. Tiny quantum fluctuations during inflation were magnified to cosmic scales, planting the seeds for galaxies and cosmic structures. Yet these fluctuations imply a branching reality, where each possible outcome leads to a different universe's birth. This coupling of quantum phenomena and cosmic expansion underlies the many worlds interpretation. Unlike classical branching, trees, the quantum multiverse embodies a fractal structure, where every event unfolds into a web of possibilities. The boundaries between universes are not walls, but subtle divergences in the cosmic wave function, invisible yet eternally distinct. In this picture, the universe is a vast quantum superposition, a boundless ensemble of histories and futures existing simultaneously. The consequences extend beyond physics into philosophy and the nature of consciousness. If all possible outcomes occur, then every choice, every fleeting thought, resonates through infinite parallel lives. This vision challenges the concept of a singular self, suggesting instead a multitudes of selves, each navigating its own unique trajectory through the multiverse. But the multiverse is not confined to quantum mechanics alone. String theory, a framework seeking to unify all fundamental forces, introduces extra spatial dimensions curled into intricate shapes beyond perception. These extra dimensions, though hidden, determine the properties of particles and forces in our universe. String theory's landscape of vacua is staggeringly vast, with estimates numbering upwards of 10,500 distinct possible universes. Each vacuum corresponds to a unique set of physical constants and laws, presenting a bewildering diversity of possible realities. Our universe's particular configuration emerges as one among these many possibilities, selected perhaps by chance or by deeper principles yet to be uncovered. In some scenarios, these distinct vacua can be realized as separate universes within a grander multiverse. Eternal inflation acts as a cosmic generator, continuously producing bubble universes that settle into different vacuum states, like droplets forming in boiling water. Each bubble may possess its own physics, its own version of particles, forces, and even dimensions. This raises profound questions about the nature of reality itself. Are these universes equally real, or mere mathematical possibilities? Does existence require observation, or is reality independent of perception? Modern physics nudges us toward an unsettling yet awe-inspiring answer. Existence may be far richer and more layered than our senses reveal. Testing the multiverse hypothesis remains a formidable challenge. Direct observation of other universes is beyond our current technological reach, their distances insurmountable by any conceivable signal. However, subtle imprints might be encoded in the cosmic microwave background, ancient light from the universe's infancy. Collisions between bubble universes, if they occurred, could leave faint circular patterns or temperature anomalies in this relic radiation. Moreover, the distribution of fundamental constants across a hypothetical multiverse might be reflected statistically in the parameters we observe. If these values fall within ranges conducive to life, this anthropic selection offers indirect support to the multiverse framework, providing a context to explain the fine-tuning puzzle without invoking design. The multiverse also reframes humanity's philosophical narrative. No longer the singular crown of creation, our universe becomes part of an intricate mosaic, a single note in an infinite cosmic symphony. This perspective evokes both humility and wonder, reminding us of the vastness beyond our comprehension. In this grand cosmic theater, the multiverse is not just a scientific hypothesis, but a call to expand the horizons of thought and imagination. It invites us to consider realities where time flows differently, where the very constants of nature shift, where life, if it exists, may take forms unimaginable. It challenges the boundaries of physics, philosophy, and spirituality, weaving them into a tapestry as rich and varied as the cosmos itself. Our journey through the multiverse is a journey into the unknown, a voyage that may redefine what it means to exist. Each new theory, each new observation, is a thread unraveling the deeper fabric of reality, drawing us closer to the heart of the cosmic mystery. The exploration of the multiverse compels us to reconsider the foundations of reality, the very fabric from which existence is woven. Central to this inquiry is the question of what constitutes a universe, and how these myriad universes might relate or interact. In the traditional view, our universe is all-encompassing, bounded by a cosmic horizon that limits what we can observe or influence. Yet the multiverse challenges this view, proposing that our cosmic horizon is but a small window into a vast, possibly infinite ensemble of universes. One compelling scenario is that of brain cosmology, derived from string theory and its extension, M-theory. Here, the fundamental entities are not just strings but multidimensional membranes, or brains, floating within a higher dimensional space known as the bulk. Our universe could be a three-dimensional brain embedded in this higher dimensional bulk, alongside other brains that constitute other universes. In this framework, universes may be parallel brains, coexisting in dimensions beyond our perception, separated yet capable in some models of interacting. The interaction or collision of brains could trigger cosmic events analogous to a Big Bang, potentially spawning new universes or altering the course of existing ones. The implications are profound. Our universe's birth, evolution, and ultimate fate might be influenced not only by internal dynamics but by the motions and collisions of neighboring brains. The fabric of reality, rather than being a singular four-dimensional space-time, becomes a higher-dimensional manifold with multiple layers and interactions. Moreover, brain collisions could leave observable imprints. For example, specific patterns in the cosmic microwave background might reveal such cosmic encounters, offering a window into events beyond our universe's own history. These signatures would provide tantalizing evidence of a higher dimensional multiverse, bridging the gap between abstract theory and observable phenomena. Beyond brain cosmology, other multiverse models explore different possibilities. The mathematical multiverse hypothesis posits that all mathematically consistent structures exist as realities. In this view, every coherent mathematical description corresponds to a physical universe. Our own universe is but one such structure within this grand mathematical landscape. This radical perspective suggests that existence is synonymous with mathematical consistency. Reality is the totality of all possible mathematical objects, making the multiverse a plenitude of abstract universes, each governed by its own internal logic and rules. While more philosophical than physical, the mathematical multiverse challenges the notion of what it means for something to be real. It bridges physics and metaphysics, suggesting that the physical laws we observe are emergent from deeper mathematical truths. Across these various models, a common thread emerges. The multiverse is not a single theory but a framework of ideas. It extends from quantum branching worlds to cosmic inflation bubbles, from higher dimensional brains to abstract mathematical realms. Each perspective enriches our understanding of what reality might be, broadening the scope of scientific inquiry and philosophical reflection. The multiverse also reshapes our understanding of cosmological origins and endings. If universes are born from inflationary bubbles or brain collisions, what lies beyond the birth of our cosmos? Might the multiverse be eternal, with universes continuously emerging, evolving, and fading away? Could time itself be an emergent property within each universe, while the multiverse as a whole transcends temporal constraints? These questions beckon us toward new physics and new mathematics, challenging the limits of empirical science. They call for innovative approaches to observation and theory, leveraging the interplay between cosmology, particle physics, and quantum gravity. At the heart of the multiverse concept lies the profound humility that our universe, with all its complexity and beauty, may be but a single instance in an unimaginably vast ensemble. It invites us to embrace uncertainty and mystery, recognizing that our current understanding is a stepping stone toward deeper truths. Yet, even as the multiverse expands the cosmos beyond the observable, it also brings a renewed focus on the singularity of our own existence. Our life, our choices, and our reality gain new dimensions of meaning when seen as part of a boundless cosmic landscape. The multiverse challenges us to find wonder, not only in what lies beyond, but in the preciousness of the here and now. As the quest continues, the multiverse remains one of the most tantalizing frontiers in modern physics, a bold vision that unites imagination and rigor, science and philosophy, in the eternal search for understanding. As we delve deeper into the multiverse, the notion that multiple universes exist concurrently forces us to confront the very nature of reality and what it means to observe and measure it. Quantum mechanics, with its principles of superposition and entanglement, offers some of the most striking insights into how multiple realities might coexist, and how consciousness may play a role in collapsing these possibilities into the reality we experience. The famous Schrödinger's cat thought experiment vividly illustrates the puzzling nature of quantum superpositions, where a cat inside a sealed box can be considered both alive and dead until observed. Extending this to the universe itself suggests that countless states and configurations can exist simultaneously, branching off with every quantum event into new, divergent universes. This many-worlds interpretation proposes that every quantum event spawns a new universe for each possible outcome, resulting in a colossal, ever-branching tree of realities. Within this framework, all possible histories and futures are realized somewhere in the multiverse. Our experience is but one thread woven into this cosmic tapestry, with countless versions of ourselves living out alternate scenarios shaped by different decisions and chance events. The implications challenge our classical notions of identity and free will. If every possible choice is played out in some parallel universe, what does it mean for us to make decisions or for life to be meaningful? Some interpret this as a liberation from determinism, embracing a reality where infinite possibilities exist simultaneously. Others view it as a humbling acknowledgement of our small place within an unimaginably vast multiversal stage. Yet, the many worlds interpretation is not without controversy. It requires accepting a reality so vast and complex that it transcends direct verification. Experimental evidence for the multiverse remains elusive, making this theory more philosophical than empirical at present. Nevertheless, it provides a coherent framework for understanding the puzzling phenomena of quantum mechanics and offers a pathway for unifying quantum theory with cosmology. On the cosmological scale, eternal inflation suggests a different mechanism for multiverse creation. Unlike quantum branching, eternal inflation posits that the rapid expansion of spacetime continues indefinitely in some regions, creating bubble universes that bud off from the inflating space. Each bubble cools and forms its own Big Bang-like event, developing into a self-contained universe with distinct physical properties. These bubble universes could vary widely, differing in fundamental constants, particle types, and even dimensions. Such diversity provides a naturalistic explanation for the fine-tuning observed in our own universe. The anthropic principle comes into play here, stating that we find ourselves in a universe compatible with life simply because only such universes permit observers. This reasoning shifts the perspective from seeking a unique fundamental explanation for our universe's properties to embracing a statistical landscape where countless universes exist, and we inhabit one of the hospitable few. Though sometimes criticized for its apparent lack of falsifiability, this approach opens intriguing paths for scientific exploration, inspiring searches for indirect evidence in cosmological data. The concept of parallel universes also permeates popular culture, inspiring stories and imaginings that captivate our collective consciousness. From science fiction tales of alternate Earths to speculative narratives about multiversal travel, these ideas invite us to ponder what-if scenarios, expanding our understanding of possibility and identity. Yet, beyond fiction and speculation, the multiverse compels scientists and philosophers alike to reflect on the nature of existence, causality, and observation. It blurs the lines between physics and metaphysics, between what can be measured and what can be imagined. Efforts to test multiverse theories continue to push the boundaries of technology and theory. Observatories scanning the cosmic microwave background seek anomalies that might hint at collisions between bubble universes. Particle accelerators probe the fundamental structure of matter, hoping to uncover evidence of extra dimensions or new physics. Theoretical work strives to reconcile gravity and quantum mechanics into a cohesive framework that embraces the multiverse's complexity. Ultimately, the multiverse concept elevates our quest for knowledge to new heights. It challenges us to rethink not only the cosmos but also our place within it. Are we solitary in an immense void, or one voice in a cosmic choir of infinite melodies? The answer remains elusive, yet the journey to uncover it fuels the spirit of human curiosity and wonder. In contemplating the multiverse, it becomes essential to explore the nature of time and space themselves. Conventional understanding portrays time as a linear progression, a steady arrow moving forward, and space as a three-dimensional backdrop in which events unfold. Yet theories underpinning the multiverse challenge this simplistic view, suggesting that time and space may be emergent properties, flexible and dynamic, varying across different universes. Within quantum cosmology, the very fabric of space-time is a quantum entity, subject to fluctuations and probabilistic behaviors. In certain multiverse models, universes may have different dimensions of time or no conventional time at all. Some may contain multiple time dimensions, where causality and the flow of events operate under unfamiliar rules. Others might be timeless, where past, present, and future coexist in a timeless quantum state. This fluidity redefines causality and existence itself. If time varies from universe to universe, then cause and effect may not be universal principles, but local features unique to each cosmos. What we perceive as chronological order could be an emergent illusion arising from deeper quantum processes or the structure of the multiverse. The theory of quantum gravity attempts to reconcile general relativity with quantum mechanics, offering glimpses into how spacetime might behave at the smallest scales. Approaches like loop quantum gravity describe spacetime as a network of discrete loops, where space is granular, and time may arise from the interactions of these fundamental elements. In such a quantum fabric, universes may pop into existence through quantum tunneling or fluctuations, bridging the gap between nothingness and something. These birth events hint at a multiverse where universes are ephemeral bubbles, emerging and dissolving within a greater quantum foam. Beyond physics, these insights influence philosophical debates on existence. If time and space are not absolute, our perception of reality as a fixed stage is upended. We become travelers, not in a static universe, but in a dynamic, evolving multiverse, where realities bloom and fade like ephemeral flowers. Another intriguing dimension emerges when considering information and entropy within the multiverse. The second law of thermodynamics states that entropy, a measure of disorder, tends to increase in closed systems, giving time its arrow. Yet in multiverse cosmology, entropy may behave differently across universes. Some universes could have reversed entropy flow, where order arises spontaneously, or others may exist in a state of maximum entropy, resembling a cosmic equilibrium. These possibilities challenge our understanding of thermodynamics and suggest that fundamental laws may be local rather than universal. This interplay between entropy, time, and information invites a reevaluation of the meaning of existence and the evolution of complexity. It hints at multiversal cycles, where universes undergo birth, growth, decay, and rebirth on scales beyond human comprehension. The multiverse concept also influences the search for a theory of everything, a comprehensive framework that unites all physical phenomena. String theory and M-theory stand as promising candidates, envisioning a cosmos of vibrating strings and membranes whose patterns manifest as particles and forces. In these frameworks, the multiverse arises naturally from the diversity of solutions to the underlying equations. Each vacuum state corresponds to a universe with its own physics, painting a grand landscape of possibilities. Understanding why our universe occupies its specific point in this landscape remains a central question, intertwining physics, philosophy, and cosmology. The multiverse pushes science to embrace complexity and ambiguity, encouraging new methods of inquiry and experimentation. As technology advances, tools like gravitational wave detectors, particle colliders, and cosmic observatories may reveal subtle hints of multiversal interactions. Beyond the technical, the multiverse inspires profound reflection on human significance. In a cosmos of infinite variation, our experiences become simultaneously unique and part of a vast cosmic ensemble. This duality enriches the human story, blending science with existential wonder. The journey into the multiverse is a voyage into the deepest mysteries of reality, a pursuit that challenges intellect and imagination alike. It reminds us that the quest for knowledge is boundless, echoing through the infinite corridors of possibility. The philosophical implications of the multiverse concept stretch far beyond the boundaries of physics, touching on age-old questions about existence, consciousness, and meaning. If countless universes exist, each with its own laws, histories, and versions of ourselves, what does that say about identity and the nature of the self? The notion of parallel selves living out every possible decision confronts us with a radical multiplicity of being. We might imagine infinite versions of you and me, each experiencing a different path, making different choices, and facing distinct outcomes. This plurality challenges the classical idea of a singular, continuous self, replacing it with a branching tree of identities. Some philosophers argue that this fragmentation dilutes the significance of individual experience, rendering personal identity a fleeting construct among infinite alternatives. Others find liberation in this vision, embracing the possibility that our choices reverberate across many realities, giving life a cosmic depth and interconnectedness. The question of consciousness becomes central here. Does consciousness itself branch with every universe? Is each parallel self a unique conscious agent, or is there a deeper unifying awareness transcending individual realities? These questions touch on the hard problem of consciousness, how subjective experience arises from physical processes, and the multiverse adds a new layer of complexity. Some theories suggest consciousness might be a fundamental aspect of reality, not confined to a single universe but woven through the multiverse's fabric. This perspective invites the possibility of shared consciousness or entanglement across parallel worlds, where experiences resonate beyond the bounds of a single cosmos. In addition, the multiverse invites reconsideration of moral and ethical frameworks. If every possible outcome is realized somewhere, how do we weigh responsibility or consequence? The existence of universes where different choices are made complicates traditional ideas of accountability and fate. Yet this plurality also emphasizes the preciousness of conscious experience in our own universe. Even within infinite possibilities, the reality we inhabit is singular and immediate. The multiverse deepens the mystery and wonder of existence, encouraging mindfulness and appreciation for the here and now. On a scientific front, exploring these philosophical questions drives innovation and interdisciplinary dialogue. Physicists, philosophers, neuroscientists, and theologians engage in conversations that transcend traditional boundaries, seeking to understand how the multiverse shapes human understanding. The pursuit of experimental evidence continues to be a challenge. While direct observation of parallel universes may remain beyond reach, indirect clues offer hope. Gravitational waves, cosmic background patterns, or particle physics anomalies might provide windows into multiversal interactions. Theoretical advances, such as holographic principles and quantum entanglement, suggest the universe's information may be encoded in subtle ways that hint at deeper layers of reality. These insights connect with ideas of the multiverse as a holographic projection, where boundaries between universes blur. The cultural impact of the multiverse is equally profound. Stories, art, and philosophy inspired by parallel worlds invite us to explore our desires, fears, and hopes through alternative realities. They enrich our imagination and encourage empathy by highlighting the diversity of experience. In the end, the multiverse is a testament to human curiosity and the desire to grasp the infinite. It challenges us to think beyond the limits of our senses and concepts, urging us to expand our horizons and embrace mystery. As we continue to probe the cosmos, the multiverse stands as a beacon of wonder, a vision that transforms science into a grand narrative of endless possibility and discovery. Advancing our understanding of the multiverse demands pushing the boundaries of both theory and observation. Modern physics offers a suite of sophisticated tools and ideas, each contributing a piece to the complex puzzle of multiple realities. From the microscopic quantum realm to the grand architecture of cosmic inflation, the multiverse hypothesis connects the smallest scales with the largest, weaving a narrative that transcends conventional science. One crucial avenue of investigation is the study of cosmic microwave background radiation, the faint afterglow of the Big Bang. This ancient light carries imprints of the universe's earliest moments, offering a window into the conditions that shaped our cosmos. Scientists search this radiation for subtle anomalies or patterns that might hint at interactions with other universes, such as gravitational collisions or overlapping bubbles. The detection of such signals would be groundbreaking, providing empirical support for the existence of neighboring universes beyond our observable horizon. Yet these measurements are extraordinarily challenging, requiring unprecedented sensitivity and precision. Advances in satellite technology and data analysis continually improve our ability to detect faint signatures hidden in cosmic noise. On a different front, particle physics experiments at facilities like the Large Hadron Collider explore the fundamental building blocks of matter. The discovery of new particles or forces beyond the standard model could offer clues to the nature of extra dimensions or the multiverse itself. For instance, the existence of supersymmetric particles or evidence for brane worlds, higher dimensional membranes where universes might reside, could reshape our understanding of reality. Quantum computing and simulations also provide novel ways to explore multiversal theories. By modeling complex quantum systems, researchers investigate how superpositions and entanglement could give rise to branching universes. These computational experiments deepen our grasp of quantum mechanics paradoxes and open pathways toward unifying it with gravity. Mathematical physics plays a foundational role, with abstract frameworks such as string theory and M-theory generating landscapes of possible universes. These theories describe particles and forces as manifestations of tiny vibrating strings or membranes existing in higher dimensional space. Each solution corresponds to a unique universe with its own set of physical laws and constants, creating a multiverse landscape so vast that it defies full comprehension. Understanding why our universe occupies a specific point in this landscape, why its laws allow life and complexity, remains one of the greatest scientific challenges. The anthropic principle suggests that observers find themselves in universes compatible with their existence, but many physicists seek deeper, predictive explanations. The interplay between theory and observation pushes science toward new horizons. Projects designed to map dark energy and dark matter, the mysterious substances comprising most of the cosmos, may uncover phenomena pointing to multiversal effects. These dark components influence the universe's expansion and structure, and their nature remains enigmatic. Beyond physics, the multiverse hypothesis reshapes our narrative of cosmic origins and destiny. It implies that creation is not a singular event but an ongoing process, an eternal unfolding of universes within an infinite ensemble. This dynamic cosmos is alive with possibility, continuously birthing new realities that challenge our imagination. The philosophical and spiritual dimensions of the multiverse inspire renewed contemplation of human purpose and connection. In a cosmos where every possibility exists, the meaning we derive from our experiences becomes a creative act, an affirmation amid infinite potential. Ultimately, the pursuit of multiverse knowledge is a journey of humility and awe. It calls us to embrace uncertainty and wonder, recognizing that our quest to understand reality is a mirror of the infinite complexity that surrounds us. The concept of the multiverse invites us to reconsider not only the structure of reality, but also the origins of existence itself. Traditionally, cosmology sought a singular beginning, the Big Bang, as the birth of our universe and all that it contains. However, multiverse theories propose that our universe may be one bubble in a far larger cosmic ocean, where countless bubbles are continuously forming, each a universe in its own right. Eternal inflation theory expands on this by describing an unending process of rapid cosmic expansion. While inflation ended in our local region, creating the observable universe, it continues elsewhere, spawning new universes in a ceaseless fractal pattern. Each bubble universe may have distinct physical laws and constants, resulting from the different ways symmetry breaks as they form. This paints a picture of the cosmos as a dynamic, evolving ensemble where universes arise, evolve, and perhaps vanish within an ever-expanding multiversal expanse. In such a framework, the Big Bang is no longer the absolute beginning, but a local event in a grander multiversal process. From a philosophical perspective, this challenges the notion of a single creation event or a unique cosmic origin. Instead, existence becomes a continuous unfolding, where universes emerge in an eternal cycle without a definitive starting point. This raises profound questions about cause, contingency, and the nature of reality. The diversity of physical laws across universes may be immense. Some may resemble our own closely, with atoms, stars, and galaxies. Others could be drastically different, with no stable matter or familiar forces. The possibility that many universes are inhospitable to life introduces a natural selection of sorts, where only certain configurations permit complexity and consciousness. This multiverse natural selection offers a potential explanation for the fine-tuning problem, the observation that our universe's physical constants appear precisely set to allow life. Instead of invoking design or chance, the multiverse suggests that many universes exist with varied constants, and we find ourselves in one conducive to life, simply because only such universes can harbor observers. While compelling, this view remains controversial, as it challenges traditional scientific methods. The multiverse, by its nature, may be impossible to directly observe or test, residing beyond the cosmic horizon. Critics argue that this risks slipping into metaphysics rather than empirical science. Nevertheless, physicists develop indirect methods to assess multiverse hypotheses. If collisions between bubble universes occurred in the early cosmos, they might leave detectable imprints on the cosmic microwave background or gravitational waves. Such evidence would transform the multiverse from speculative philosophy to scientific theory. In parallel, developments in quantum mechanics suggest a multiplicity of realities at the smallest scales. The many-worlds interpretation, proposed by Hugh Everett, views every quantum event as splitting reality into branches, each realizing different outcomes. In this view, the multiverse is not only cosmological, but intrinsic to quantum phenomena. The overlap of cosmological and quantum multiverse ideas hints at a profound unity, where the macro and microcosmos reflect each other in an infinite tapestry of realities. This confluence challenges the traditional division between the quantum and classical worlds, inviting new paradigms in physics. The multiverse concept reshapes our worldview, suggesting that what we call reality is but one facet of a vast and intricate whole. It challenges us to expand our imagination and embrace complexity, accepting that certainty may be elusive, but wonder is infinite. As science progresses, the multiverse remains a frontier where knowledge, philosophy, and mystery converge, illuminating the boundless scope of the cosmos and our place within it. The exploration of the multiverse also invites a deeper examination of the fundamental constants of nature, the fixed numbers that govern the behavior of forces and particles in our universe. Constants such as the speed of light, the gravitational constant, and the charge of the electron define the rules by which matter interacts and structures emerge. Their precise values enable the formation of atoms, stars, and ultimately life. In the context of the multiverse, these constants may not be universal, but local parameters that vary from one universe to another. Different values could lead to universes radically different from ours, some collapsing immediately due to strong gravity, others expanding too rapidly for matter to coalesce, and still others with no stable atoms. This possibility introduces the concept of the landscape of universes, a vast, multidimensional space of all possible combinations of constants and laws. Our universe occupies a particular point in this landscape, seemingly fine-tuned to support complexity and life. This fine-tuning problem has long fascinated scientists and philosophers alike. Some view it as evidence of design or purpose, while others see it as a statistical inevitability in a multiverse containing every possible universe. The anthropic principle offers a way to understand this. We observe the constants we do because only universes with such values can support observers like us. While this reasoning does not explain why the constants have these values, it reframes the question within a broader multiversal context. The multiverse also raises questions about the nature of physical laws themselves. Are laws absolute and eternal, or do they emerge from deeper principles? Some theories suggest that physical laws are not fixed, but evolve or differ across universes, shaped by the initial conditions or vacuum states in each. In such a scenario, what we call fundamental laws might be effective rules that govern our local cosmos, but are contingent rather than universal. This shifts the goal of physics from discovering immutable laws to understanding the underlying principles that generate diverse physical realities. String theory embodies this idea by positing a vast landscape of solutions, each corresponding to different laws and constants. The challenge is to find mechanisms that select or favor certain universes over others, potentially explaining why our cosmos has its particular features. Experimental efforts continue to probe these questions. Precision measurements in cosmology, particle physics, and quantum mechanics aim to detect deviations or anomalies that might hint at other universes or new physics beyond the standard model. Despite formidable challenges, the quest to understand the multiverse is a powerful driver of scientific progress. It pushes theorists to develop new mathematics and frameworks, inspiring experiments that expand our knowledge of the cosmos. Moreover, the multiverse stimulates profound reflection on human existence. In an infinite ensemble of universes, every possibility exists somewhere, including versions of ourselves living different lives. This vision blurs the line between science and philosophy, inviting us to contemplate the nature of choice, destiny, and reality itself. Ultimately, the multiverse challenges us to embrace a cosmic perspective that is both humbling and exhilarating. It expands the horizon of what is possible, transforming our understanding of the universe from a solitary realm into an infinite sea of worlds. As we delve deeper into the multiverse concept, it becomes essential to explore how the framework intersects with quantum mechanics, the theory that governs the behavior of particles at the smallest scales. Quantum theory reveals a world that defies classical intuition. Particles exist in superpositions, occupying multiple states simultaneously until measured or observed. The many worlds interpretation, formulated by physicist Hugh Everett in the 1950s, provides a bold and elegant explanation for this quantum strangeness. Instead of collapsing a wave function into a single outcome, this interpretation posits that every possible outcome of a quantum event actually occurs, each in its own branching universe. In this vision, the multiverse is constantly branching and proliferating as particles, atoms, and observers make countless quantum decisions. Every moment of existence generates a cosmic tree of realities, each equally real yet separated by non-communicating branches. This interpretation solves certain paradoxes in quantum mechanics by removing the need for wave function collapse, a process that has troubled physicists for decades. Instead, all possibilities coexist in a vast, branching multiverse. However, this raises profound questions about identity and experience. If every decision leads to new universes, does each you in each branch experience a different reality? How do we reconcile the subjective unity of consciousness with this multiplicity? Some philosophers and physicists suggest that consciousness itself splits or branches, creating multiple streams of experience. Others propose that consciousness is fundamentally unified and only appears divided due to the limits of perception. The many worlds view also impacts our understanding of probability and fate. Instead of chance collapsing reality into one outcome, all outcomes occur, making the concept of probability a measure of relative branch weight or thickness, rather than a singular future. Critics argue that the many worlds interpretation is metaphysical, lacking direct experimental testability. Yet, it remains one of the most coherent and widely discussed interpretations of quantum mechanics, deeply intertwined with multiverse ideas. Further, the interplay between quantum mechanics and gravity remains a frontier. A quantum theory of gravity, still elusive, could unify these concepts and provide a deeper understanding of the multiverse's nature. This intersection is the domain of quantum cosmology, which attempts to describe the universe's birth and evolution using quantum principles. In this framework, the universe itself may emerge from a quantum fluctuation or tunneling event, initiating its own branch in the multiverse. Such models blur the line between micro and macro, suggesting that the quantum multiverse and the cosmological multiverse are facets of a single underlying reality. This unity encourages new approaches to long-standing puzzles such as the origin of time, the arrow of entropy, and the nature of space-time. Exploring these connections demands the integration of physics, mathematics, philosophy, and even information theory. Concepts such as holography, where information about a volume of space is encoded on its boundary, point toward a radical rethinking of reality's fabric. The multiverse thus challenges the very foundation of what it means to exist and to observe. It invites us to embrace uncertainty and multiplicity, while seeking coherence and meaning amid infinite possibilities. As the frontiers of physics and philosophy converge, the multiverse remains a beacon for inquiry, illuminating the vastness of reality and our quest to understand our place within it. In considering the multiverse, it is important to explore the potential implications for cosmology and the ultimate fate of our own universe. The idea that our cosmos is just one among many has profound consequences for how we understand its beginning, evolution, and eventual end. The Big Bang, traditionally viewed as the singular moment of creation, becomes instead a localized event within an endless cosmic landscape. If eternal inflation persists beyond our observable universe, new bubble universes could be constantly forming, each undergoing its own Big Bang and cosmic evolution. This ongoing process suggests that creation is not a unique occurrence, but a perpetual phenomenon, with universes continuously budding off from the inflating multiverse. Our universe is then part of a vast and dynamic ensemble, each member with its own trajectory through space and time. The fate of our universe may be similarly open-ended. Current observations indicate that cosmic expansion is accelerating, driven by mysterious dark energy. If this acceleration continues, galaxies will eventually drift beyond each other's horizons, leading to a cold, dark, and empty cosmos. Alternatively, if dark energy changes or dissipates, the universe could collapse in a big crunch or transform through unknown processes. Within a multiverse framework, all such scenarios may be realized in different universes. Moreover, some multiverse theories entertain the idea that universes can interact or influence each other, albeit weakly or indirectly. The collisions between bubble universes might trigger cosmic events, or higher dimensional effects could ripple through the multiverse fabric. These interactions could leave observable signatures, such as distortions in the cosmic microwave background or gravitational wave bursts. Detecting such evidence would revolutionize cosmology and provide a glimpse beyond our cosmic horizon. On a more speculative level, some hypotheses propose that advanced civilizations might one day manipulate or create universes, harnessing the fundamental processes of cosmic inflation or quantum fluctuations. This notion, blending physics and futurism, challenges the limits of possibility and invites philosophical reflection. The multiverse also reframes our understanding of cosmic coincidence and chance. Why do the laws and constants in our universe permit life and consciousness? Instead of invoking design or randomness, the multiverse offers a statistical landscape where countless universes exist with diverse properties, and observers emerge only where conditions allow. This statistical perspective aligns with naturalistic explanations and connects cosmology with fundamental physics, bringing coherence to deep questions about existence. Yet, the multiverse hypothesis remains one of the most controversial and challenging ideas in modern science. Its implications touch on philosophy, metaphysics, and the limits of scientific inquiry. Critics caution against over-reliance on untestable theories, emphasizing the need for empirical grounding. Nevertheless, the multiverse continues to inspire and provoke, driving research and imagination. It exemplifies the boldest ambitions of science to explore not only what is but what might be, stretching the boundaries of knowledge and thought. As we probe deeper into the cosmos and the quantum realm, the multiverse stands as a profound frontier, inviting us to ponder infinity, possibility, and the essence of reality itself. The notion of a multiverse challenges the very fabric of what we consider reality, introducing a scale and complexity that dwarfs the singular universe model. This expansion of perspective encourages us to rethink fundamental concepts such as space, time, and existence. One fascinating area where the multiverse idea manifests is in string theory, a leading candidate for a theory of everything. String theory proposes that the fundamental particles we observe are not point-like dots, but tiny vibrating strings whose modes of vibration determine particle properties. However, string theory predicts an enormous landscape of possible solutions vacua, each corresponding to a universe with its own set of physical laws and constants. The number of these possible universes can be unimaginably vast, perhaps on the order of 10^500, making our universe a single point in an almost infinite multiversal space. This string landscape arises because extra-spatial dimensions, beyond the familiar three, can be compactified in countless ways, shaping the physics of each universe uniquely. The shape and size of these dimensions influence forces, particle masses, and constants. While this richness provides a framework to explain the fine-tuning of our universe, it also presents a challenge: how to select the universe we inhabit from this vast ensemble? This is sometimes called the vacuum selection problem, a puzzle at the heart of modern theoretical physics. The anthropic principle is often invoked here, suggesting that only those universes with parameters compatible with life are observed, as we could not exist otherwise. While controversial, this reasoning provides a naturalistic way to understand why our universe has its specific laws amidst a cosmic sea of possibilities. Another approach involves dynamical mechanisms or probabilistic arguments that might favor certain vacua during cosmic evolution. Understanding these selection processes remains an active area of research. String theory's multiverse concept also intertwines with quantum gravity efforts, including the holographic principle. The holographic principle posits that the information content of a volume of space can be encoded on its boundary, hinting at a deeper, more fundamental description of reality. Such ideas suggest that space-time and gravity may emerge from more basic quantum informational building blocks, potentially uniting quantum mechanics and general relativity. This emergence challenges the classical view of space and time as fundamental backgrounds, revealing them instead as collective phenomena arising from underlying quantum degrees of freedom. The multiverse, then, is not merely a collection of separate universes, but possibly a manifestation of deeper underlying principles of information, symmetry, and dynamics. This perspective reshapes the quest for a unified theory, inspiring new mathematical frameworks and physical insights. It encourages viewing our universe as part of a grander, interconnected structure, where boundaries between universes, dimensions, and physical laws blur. As researchers push forward, they harness powerful tools from quantum field theory, geometry, and computational methods, seeking clues about the multiverse's architecture and origins. The journey is as much philosophical as scientific, inviting us to explore profound questions about existence, knowledge, and the limits of human understanding. The multiverse remains a captivating and evolving idea, one that continues to redefine our cosmic horizon and the meaning of reality itself. The multiverse concept also invites us to revisit the fundamental notion of time. In our familiar experience, time flows in a linear, unidirectional manner, from past to future, anchoring our perception of causality and change. Yet when we extend our gaze to the multiverse, this intuitive understanding becomes less certain. Some multiverse models suggest that time itself may be an emergent phenomenon, arising from deeper, timeless quantum structures. In certain formulations of quantum gravity, time loses its fundamental status and appears only as an approximate parameter within local universes. This idea challenges the classical picture and calls for a new framework to describe reality without relying on time as a primary coordinate. Instead, time may emerge from correlations between quantum states or through the entanglement of subsystems. If time is emergent, then each universe in the multiverse might possess its own distinct temporal structure. Some universes could have time flowing differently, or even lack a clear temporal direction altogether. This diversity complicates how we conceive of causality and sequence across the multiverse. Moreover, the arrow of time, the observed directionality from order to disorder, is closely tied to entropy and the second law of thermodynamics. Understanding why entropy increases and time flows in one direction remains an open question in physics. Within the multiverse, it's conceivable that different universes have varied entropy conditions and temporal arrows, or even reverse time flows. Such possibilities stretch our imagination and require new principles to describe temporal phenomena universally. These considerations also intersect with cosmological models of the universe's origin and evolution. Some theories propose cyclic universes, where cosmic epochs repeat, or bouncing cosmologies, where a collapsing universe rebounds into a new expansion. If such scenarios hold, time's nature becomes cyclical or multidimensional, integrating past and future in novel ways. These models could be embedded within the multiverse, with different bubbles experiencing distinct temporal regimes. Quantum mechanics adds further complexity. Quantum entanglement connects particles across space and time, hinting at non-local relationships that challenge classical causality. These phenomena might offer clues to a more profound temporal structure. Philosophically, reconsidering time in a multiverse context invites reflection on free will, determinism, and the experience of existence. If all possible futures unfold somewhere in the multiverse, what does this mean for choice and identity? While empirical investigation of time's fundamental nature is challenging, advances in theoretical physics, cosmology, and quantum information continue to shed light on these deep issues. The multiverse thus acts as a catalyst for reimagining time, not as a fixed backdrop but as a dynamic, context-dependent aspect of reality, shaped by quantum and cosmological processes. This shift in perspective opens new pathways for understanding the universe's origin, structure, and destiny, and ultimately our place within the vast, timeless multiversal expanse. Another profound implication of the multiverse is its potential to resolve enduring mysteries in physics by providing a broader context for physical laws and constants. One such puzzle is the fine-tuning problem. Why do the fundamental constants of nature appear so precisely calibrated to allow the existence of stars, planets, and life? Constants like the strength of the electromagnetic force, the masses of elementary particles, and the cosmological constant seem delicately balanced within narrow ranges. Slight deviations could render the universe lifeless or radically different. In a traditional single-universe view, this fine-tuning can feel mysterious or even miraculous, prompting various explanations, from divine design to unexplored physical principles. The multiverse offers an elegant, naturalistic resolution. If countless universes exist, each with varying physical constants, then it is no surprise that at least one, like ours, possesses the right conditions for life. This anthropic reasoning suggests that observers can only arise in universes compatible with their existence, explaining why we find ourselves in such a finely tuned cosmos. Although controversial, the anthropic principle gained prominence especially in the context of eternal inflation and the string landscape, where vast numbers of universes differ in fundamental parameters. Moreover, the multiverse idea opens new avenues for understanding the cosmological constant problem. The cosmological constant, which drives the accelerated expansion of our universe, is incredibly small, yet non-zero. Quantum field theories predict a value vastly larger than observed, creating a profound discrepancy. If the cosmological constant varies across the multiverse, universes with large values would expand too rapidly for structures to form, while those with values near what we observe allow galaxy and star formation. Our universe's small cosmological constant is then a statistical necessity within the multiverse, avoiding the need for unexplained fine-tuning or new physics. These insights underscore the multiverse's explanatory power, reframing apparent coincidences as natural outcomes of cosmic diversity. Beyond constants, the multiverse also challenges the universality of physical laws. Could the laws themselves differ across universes? While the mathematics of physical laws suggests consistency, variations in symmetries, particle types, or interaction strengths may exist. If so, the multiverse embodies a vast landscape of physical realities, each governed by its own principles, inviting us to reconsider the idea of laws of nature as absolute. This pluralism has philosophical implications, expanding the scope of natural science and questioning whether our universe's laws are special or typical. In sum, the multiverse not only enriches our cosmological understanding, but also reshapes fundamental questions about law, chance, and existence, presenting a paradigm where diversity is the cosmic norm. Delving deeper into the multiverse landscape, one encounters the intriguing concept of quantum branching, closely tied to the many worlds interpretation of quantum mechanics. This interpretation proposes that every quantum event, every measurement, or interaction that could yield different outcomes, causes the universe to split into multiple non-interacting branches, each realizing one possible result. Unlike classical collapse interpretations, which suggest a single outcome is realized while others vanish, many worlds holds that all possibilities persist simultaneously, creating an unimaginably vast and continually branching multiverse. For example, when a particle passes through a double slit, the universe branches into multiple realities, each with the particle taking a different path. These branches evolve independently, forming a complex quantum tree of parallel histories. This view elegantly removes the mystery of wave function collapse and offers a deterministic framework for quantum phenomena, albeit at the cost of an enormous proliferation of worlds. In the many worlds multiverse, every choice, chance event, and quantum fluctuation spawns new realities, leading to an effectively infinite ensemble of universes, encompassing all possibilities. This raises profound questions about identity, probability, and reality. If all outcomes occur, what meaning does probability have? How do we reconcile our experience of a single, consistent reality? Physicists and philosophers have developed frameworks to understand subjective probabilities and decision-making within this branching structure, but debates continue. Many worlds also challenges the classical notion of a singular past and future, suggesting instead a richly interconnected web of timelines. While difficult to test directly, many worlds is supported by the mathematical consistency of quantum mechanics and has gained respect as a serious interpretation. The concept also aligns intriguingly with cosmological multiverse ideas, suggesting that quantum branching could operate not only at microscopic scales, but influence the very fabric of universes. If quantum branching extends to cosmic scales, the multiverse includes variations not just in quantum outcomes, but entire cosmic histories, each unfolding with different initial conditions or laws. This union of quantum and cosmological multiverses offers a compelling, if complex, vision of reality as a vast, layered structure of possibilities, interconnected yet causally isolated. It suggests that reality is far richer and more intricate than our everyday experience reveals, inviting us to explore new realms of understanding and existence. Exploring the multiverse draws us ever closer to the boundaries of metaphysics, where physics intersects with philosophy, and the distinction between empirical science and speculative inquiry begins to blur. Here, the very notion of reality demands reevaluation, not as a singular observable entity, but as a layered and possibly infinite structure of interwoven possibilities. At the center of this reflection lies the observer, the sentient witness who experiences a world seemingly stable and consistent. In a multiverse filled with alternate laws, varied initial conditions, and infinite branching paths, what defines the observer's place? What makes this version of reality feel more real than others that may exist in parallel, even if imperceptible? Some interpretations suggest that consciousness itself plays a role in selecting or navigating branches of the multiverse. Though speculative, this idea draws from quantum measurement theory, where observation is a key element in the transition from potential to actual. In such a framework, reality is not passively inhabited, but actively co-constructed through awareness and interaction. This leads to provocative ideas such as participatory cosmology, where the universe and perhaps the multiverse only comes into being as it is observed and measured by conscious entities. Though not embraced by mainstream physics, such perspectives echo ancient philosophical traditions in which mind and cosmos are deeply intertwined. Furthermore, the multiverse invites us to reconsider identity and the self. If countless versions of an individual exist, each shaped by divergent outcomes, what does it mean to be you? Is identity bound to a single timeline, or does it extend across branches, connected by deeper patterns of memory, choice, and consciousness? Some thinkers propose a meta-self, a composite awareness spanning multiple realities, though fragmented and inaccessible from within any single universe. While purely hypothetical, such concepts probe the limits of self-knowledge and the architecture of mind. In more grounded terms, the multiverse challenges anthropocentric views, decentering humanity from the cosmic narrative. In a universe already vast beyond comprehension, the addition of countless others reduces our physical significance even further. Yet paradoxically, this vastness can also inspire awe and humility. The realization that reality may be so expansive, so intricate, and so rich in variation underscores the preciousness of conscious experience, the rarity of life, and the value of each fleeting moment. Within this context, questions of meaning become more pressing. If everything that can happen does happen somewhere, does that dilute meaning, or does it enrich it? Does the existence of infinite versions of a story lessen the significance of anyone? Or does it suggest that every possibility is a sacred expression of the whole? These philosophical tensions are not mere abstractions. They influence how we think about purpose, morality, and the structure of knowledge. In a multiverse, ethics might not only concern actions in this universe, but ripple outward into the unknown, prompting responsibility for a broader web of reality. Even the scientific method faces new frontiers. Traditional science is built on testability, prediction, and falsifiability. But how does one test for the existence of universes forever out of reach, causally disconnected from our own? Physicists seek indirect evidence through cosmological observations, quantum statistical models, and consistency with established theory. But empirical certainty may remain elusive. In this, the multiverse resembles past scientific revolutions, where new paradigms initially exceeded observational capabilities, only to be confirmed decades or centuries later. The challenge is to balance rigor with imagination, skepticism with openness, as we extend the reach of inquiry to cosmic scales. The multiverse may remain partially veiled, yet its conceptual power transforms our understanding of space, time, and being. In embracing the multiverse, we do not escape the search for truth. We expand it. We redefine the universe not as a singular narrative, but as a chorus of realities, each a verse in an eternal, unfolding epic. One of the most captivating aspects of the multiverse theory is its potential impact on the quest for a theory of everything, a comprehensive framework that unifies all fundamental forces and particles into a single coherent description. For decades, physicists have sought such a theory, hoping to reconcile the seemingly incompatible frameworks of quantum mechanics and general relativity. String theory emerged as a promising candidate, proposing that the fundamental constituents of reality are tiny vibrating strings whose modes of vibration correspond to different particles. However, string theory brought its own surprises, revealing a vast landscape of possible solutions, on the order of 10, 500 or more, each representing a distinct universe with unique physical laws and constants. This staggering diversity within the string landscape suggests that our universe is but one of many in an immense multiverse, where different vacuum states define different low-energy physics. The multiverse arising from string theory shifts the search for a single, unique theory of everything to a quest for a framework that explains the distribution and statistics of all possible universes. This paradigm implies that the fundamental laws themselves might be environmental or contingent rather than absolute, varying from one universe to another within the greater multiverse. Additionally, loop quantum gravity offers another approach to quantum gravity, emphasizing discrete quantum geometry rather than strings. Though differing in methodology, it also suggests a complex structure of spacetime at the Planck scale, possibly compatible with multiverse ideas. In seeking to understand the multiverse through these theoretical frameworks, physicists are developing new mathematical tools and conceptual models, including higher dimensional spaces, branes, and holographic principles. The holographic principle, inspired by black hole thermodynamics, posits that all information contained within a volume of space can be described by data encoded on its boundary, hinting at profound connections between geometry, information, and quantum mechanics. Such insights reshape our conception of space itself, suggesting that spacetime might emerge from more fundamental quantum informational processes. The multiverse thereby becomes not just a cosmological possibility, but a window into the deepest structure of reality, where geometry, information, and quantum states intertwine. Furthermore, the multiverse encourages cross-disciplinary research, linking physics with information theory, computer science, and even philosophy. This interdisciplinary approach fosters new perspectives on complexity, emergence, and the nature of laws, as well as on how consciousness and observation might fit into the grand picture. Yet despite the theoretical richness, significant challenges remain. The problem of measure, how to define probabilities across infinite or vast ensembles of universes, is one of the thorniest issues in multiverse cosmology. Without a well-defined measure, making statistical predictions or comparing universes becomes problematic, undermining the explanatory power of the theory. Ongoing research strives to find natural or principled measures, often invoking anthropic considerations or new mathematical constructs. In summary, the multiverse is deeply entwined with the frontier of theoretical physics, shaping and challenging the pursuit of ultimate understanding. It invites us to reconsider the goals and methods of physics, acknowledging that the cosmos may be far richer and more varied than we ever imagined. As we venture further into the implications of the multiverse, the notion of time itself comes under scrutiny. Our everyday experience treats time as a linear progression, from past through present to future, an inexorable flow that orders events and memories. But modern physics reveals time to be far more subtle and enigmatic. In relativity, time is woven together with space into a four-dimensional fabric, space-time, where the sequence of events depends on the observer's frame of reference. In quantum mechanics, time evolution is governed by probability amplitudes, allowing multiple potential futures to coexist until measurement. Within multiverse frameworks, time may not be a universal, absolute parameter, but a local, emergent property. Some universes may have fundamentally different temporal structures, or even no clear notion of time as we understand it. Eternal inflation suggests a multiverse that is eternally generating new universes in a timeless metaspace, where time in individual universes is a secondary feature. The many worlds interpretation posits a branching structure of quantum histories, where multiple futures unfold simultaneously, rather than a single deterministic path. This challenges the classical arrow of time and raises questions about causality, memory, and the flow of experience. If countless universes exist, each with its own timeline, how does one define cause and effect across them? Are there higher dimensional meta-times coordinating these realities, or is such a notion meaningless beyond our universe? Moreover, the multiverse may offer insights into the problem of entropy and the second law of thermodynamics, which governs the unidirectional increase of disorder in closed systems. Why did our universe start in such a low entropy state, enabling complexity and life? Some theories suggest that multiverse dynamics or cyclical cosmologies could naturally reset entropy, creating rebirths of universes with fresh temporal arrows. These ideas intersect with philosophical questions about the nature of existence and becoming. If time is emergent or variable, what does it mean to exist now? Can timelessness or multiple temporalities coexist within a grander reality? While current physics cannot yet fully answer these questions, they reflect the transformative power of the multiverse concept. It demands a rethinking of time, not as a simple backdrop, but as a dynamic and diverse phenomenon. In embracing this, we expand not only our scientific understanding, but our conceptual framework for existence itself. Finally, as we reach the frontier of our exploration, the multiverse invites us to reflect on the human spirit, our place in this vast and intricate cosmos. Confronted with the possibility of countless parallel realities, each with variations of life, history, and choice, one might feel overwhelmed or diminished. Yet the multiverse also inspires profound wonder and humility. It reminds us that our universe, with its delicate balance of forces and constants, is part of an immense cosmic tapestry woven from infinite threads of possibility. Our existence, fragile and fleeting, is simultaneously unique and connected to a greater whole beyond comprehension. The multiverse challenges us to embrace uncertainty and complexity, to find meaning not in certainty or singularity, but in the richness of possibility. It invites curiosity, openness, and a deeper appreciation for the mysteries that lie beyond our current understanding. Science, philosophy, and imagination converge in this endeavor, each illuminating facets of reality and expanding the horizons of human knowledge. The journey into the multiverse is ongoing, an invitation to explore, question, and dream. It is a testament to our enduring quest to comprehend the cosmos and ourselves. In the endless dance of worlds, where every choice and chance creates new realities, we find a mirror for the infinite potential within each of us. To contemplate the multiverse is to glimpse the boundless creativity of nature and the profound interconnectedness of all things. As we stand at the threshold of these revelations, we are called not only to understand but to marvel, to wonder, and to cherish the enigmatic beauty of existence. The multiverse is not just a scientific hypothesis, it is a story of possibility, discovery, and the unending pursuit of truth. Thank you for joining this exploration. If you found this journey inspiring, please like and share, and continue to seek the wonders that lie beyond the stars.